for this exercise. So the area of our interest, as you see here with this color, that means an irrigation land which is located on the border between United States and Mexico. I don't know if it is visible for you guys. This yellow line is the border line between the two countries, and our interest area is an irrigation land. That's why the file name in the shapefile is called irrigation 4, because this is irrigation 4. They do have their own groups in order to group different irrigation areas. So they do have around 22, but we are going to model only this irrigation 4. Besides this irrigation 4, in the eastern side there is a Colorado River. That Colorado River which flows from upside direction toward Mexico, and lastly it will join the Gulf of California, which is the ocean. And also here along the yellow line there is a canal which is called All American Canals, which flows and take water in the upper direction. So you have to consider that one also, because it will be useful for us in order to take it as one of the boundary conditions. And there are also other things in which you have to consider as a boundary conditions. So when you enlarge the interest area, it seems like this. This is the shapefile, and we do have all American colors with this red line, and similarly we do have the Colorado River with this yellow zigzag lines. So having that, the general geographic setting and the hydrostratigraphic setups of this example was put on the blog. I already gave you agualabs.edublogs.org, so you can easily find and you can read it there. But to make it simple, the hydrostratigraphic setup is, it has only 3 layers. The upper layer is a sandy layer unit which has a 50-meter depth, and the middle layer, which is a silty clay unit, again it has also 50 meters, and the last unit, which is a lower sand unit, again which has a depth of 50 meters from 0 to 50 meters. And there is an impervious clay unit at the end. Then in the eastern direction or in the northeast directions, we do have again the Colorado River, in which we will consider it later as maybe a constant head boundary. So if we have 3 layers, we have also the properties of each layer. That means the hydraulic conductivity. The hydraulic conductivity for the first layer can be taken as 3 times 10 raised to minus 5. For the second layer, 10 raised to minus 7. And for the last layer, 3 times 10 raised to minus 5 meters per second. And we are also assume that all the model layers are hydraulically homogeneous and also isotropic. It means that we have Kx, which is approximately equal to Ky. That is isotropic characteristics of the aquifer. Regarding the boundary condition, we are asked to assume those 4 boundary conditions. The boundary conditions in the northeast direction, that means to refer the Colorado River, we are going to use a constant head boundary or a variant head boundary conditions, in which the head maybe will vary at the time. But on the north, like I said, there is a canal which flows along the border line, which is a yellow line, in which from that canal is expected to be there is a seepage toward the aquifer. Then imagine how we can represent this boundary condition. If there is a seepage along the north towards our modeling area, so you have to think which boundary conditions are we going to use, or how we can simulate this all-American canals, which has a bigger flow magnitude, into our model. And On the south direction, there is a hydraulically connection or a hydraulic connection between our modeling area and the outside area. That's why we are going to assume a general head boundary, which is GHB, a GHB boundary in MODFLOW. And maybe we can assume the western direction as a no-flow boundary, but in reality, it's not a no-flow boundary because, again, there is an alluvium soil here, and there is also a hydraulic connection between our model area and outside. So, in reality, it should be assumed as general head boundary. But for this simple exercise, let me assume the western side as a no-flow boundary. So regarding the boundaries, again, it's given that a seepage in all American canal is around this number. This is a very big number, meter cube. This thing is. Yeah, so to simulate the injection well, we have this value. And similarly, to use a constant head boundary, it's already given that a constant head of 100 meters. But later, I tried to change this value because we are asked to simulate from 1996 up to 2010. So I was trying to include a different heads like 100 and 88. If you check the blog, is already updated, so you can get those values. So on the blog, it says use a constant head of 100 meter and 88 meter. That means 100 meter for the years 2000 2006 and 88 meter for the year 1996 to 2000. And similarly, for a general head boundary, it's given that we have a head of 100 meter and a head of 88 meter, and also the conductance value is 0.02 and also 0.03. And this one will be 88 meter and 100 meter, and again this one will be 88 meter and 100 meter. That means from 1996 to 2000, we will use 100 meter, and from 2000 to 2006, we will use the value of 88 meters in the modeling simulation. The package that we are going to use are the recharge package, in which we do have the recharge rate and also the recharge location. And similarly, evapotranspiration rate, again, we do have the EBT rate, the EBT surface, and also the evapotranspiration depths. Those values are similar to the previous exercise. And we are going to use also the well package. Yes. So the well package, I already provided you to download the shape files. I believe you have it already. So there are numerous wells on the top of our study area, and for each and every wells, we do have a pumping rate from 1995 up to 2006. So we are going to use those pumping rate values, and we will see that in ArcMap which values are included inside the shapefile. So you do have a polygon shapefile with the file name irrigation unit 4, and also you do have a point shapefile that is the groundwater well. Again, I already provided you the digital elevation models of that area. Why we need the digital elevation model? If you remember, still now on those previous exercise, we assumed that the top and the last surface of our aquifer was flat. If you remember, it's just flat on the top, but that's not the reality. The reality is you should show the exact topographic surface of that area, and it should be shown also on the cross sections in the MODFLOW or in the ModelMuse graphical user interface. So today I will show you how we can import a digital elevation model into a Model Muse window in order to simulate the model top of this steady area. So we are asked to run an annual transient model, keep in mind, from 1995 to 2006. And here we are going to assume the initial head as a model top, and the specific storage is going to be 8 times 10 raised to minus 2. So we are asked to calculate the hydraulic head distribution, the water level, the water budgets, and also we are asked to see the relationship between these surface water, groundwater interactions on the water budget. So please open your ArcMap and let me see what type of information do we have before using and opening this Model Muse and MODFLOW window. So open your ArcMap and add all the shape files that I provided you. Add them on ArcMap window. Add the shapefile of your study area in the ArcMap. So maybe you can click on the plus sign and go to your file location. In my case, the file is located inside MODFLOW example 4. Inside MODFLOW example 4, this irrigation unit 4.shp is the shapefile that I'm going to use it. So I can click on irrigation unit 4.shp and add. It means this is the shapefile that I am going to model. And similarly, add from the same folder that I provided you, which has a file name well.shp. Those are the groundwater wells which extracted water from the aquifer for the irrigation purpose. So add them. As you see here, there are so many. There are so many groundwater wells. So they are around maybe 96, imagine. So this area only has 96 groundwater well which is extracted, and those are for irrigation purpose. Maybe you can visualize what types of attribute tables do we have, or what type of information do you have inside the attribute tables of the well shapefile. Maybe you can right click on the well and click on open attribute table. Look, you have around 96 or 97 groundwater well which are extracting your aquifer or the aquifer of the steady area. So as you heard, they have longitude and latitude, that is the locations of each groundwater well, and those values, as you see, starting from F4 up to maybe F15, they are extractions. That means the discharging of each well annually. As you see, all of them are negative. By meaning negative, they are just discharging or extracting water from the aquifer. To make it simple, this F4, the column name F4 is the extraction for the year 1995, because we are going to simulate from 1995 to 2006, yes. And F5 is 97, and similarly F6 is 98, and the last one is 2006. So having that in mind, maybe we can add also the digital elevation model that I already provided you, just to see what is the size or the extent of our digital elevation model. So in the example for folder, we do have also DEM of the area. So add the DEM of the area and you will see what is its extension. So maybe I can click yes, and I will see what will happen. It's just forming a pyramid. Then, if you examine this digital elevation model, you can easily visualize there is a river which is flowing this side, no? And that river is Colorado River. That's why we are going to assume this area as a constant head boundary. So next, what we are going to do is we will open our Model Muse window and we can import also shape file, and maybe we can build our model. But before that, I try to again produce those constant head and also general head boundary shape files. I think if you saw the blog, I already put it, but maybe if you saw it maybe 2 days or 3 days back, there is no such an information. I try to put this constant head boundary shape file and general head boundary shape file. If you remember, those boundaries are the boundary from here to here in the red, that is a constant head. And similarly, the general head boundaries are from this point up to maybe this point. So what I was doing, I opened it in ArcMap and I tried to produce the shapefile. And those are the shapefile that I produced for a general head boundary and also a constant head boundary. That means the shapefile. And similarly, maybe let me make it red and this shapefile. You know, sometimes in Model Muse, it's not that much good like to put your shapefile, that is your object, by clicking in each and every grids, but rather it's maybe recommendable to produce a shapefile by using your ArcMap window and you will import it in Model Muse window. Then I try to also include the informations inside the general head boundary, that means the head and the conductance value. So maybe I can right click here and open attribute table. So in that case, you do have the hydraulic head, which is 100 from 2000 to 2006, from the year 2000 to 2006. And from the year 1996 to 2000, we do have hydraulic head of 86. And the conductance value for the year 1996 to 2000 is 0.002. And from 2000 to 2006 is 0.03. And similarly, for a constant head boundary, again, we do have a constant head of 88 for the year 1996 to 2000 and 100 for the year 2000 to 2006. So those are the values that we are going to use in Model Muse window. So I will show you how we can use those parameters in Model Muse window. So in general, we are going to use recharge package, evapotranspiration package, well package to simulate those groundwater wells, and again another well package to simulate the injection well in the north, a constant head or CHD package here to simulate the Colorado River, a general head boundary package to simulate the connection between our modeling area in the outside world and a no-flow boundary maybe in the west directions. So open your Model Muse window if you are okay with that. Open your Model Muse window and we are going to build our model. So double click on Model Muse if you have it as a shortcut, or if not, go to Start and Model Muse, then you can open the Model Muse window. So we are going to create a new MODFLOW model. So click here, new MODFLOW model. and click on create a new model flow model because we are going to build a new model. Next, then maybe you can specify the model description as maybe exercise 4. If not, maybe you can leave this part and put the simulation date today and click next. Here is the place where we are going to specify the aquifer types. How many aquifers do you have and how many numbers of layers, etc. So if you remember, in the exercise, we do have 3 numbers of layers, which is the upper sandy layer, silty clay layer, and the last one is a lower sandy unit. So the numbers of layer is 3. I think the default is okay, but you have to write the name. The model top is a model top, but the upper aquifer is upper sandy unit, right? Upper sandy unit, and the middle one is silty clay unit, silty clay unit, and the last one is the lower sandy unit again, lower sandy unit. And as you remember, the elevations of each aquifer is 15 meter. So maybe if we assume the model top as 0, that means the upper sandy unit has a minus 15 depths, and the silty clay unit again minus 15 depths. 15 plus 15 is 13, and the last one maybe will have a 45, which is a 15 meter depth again. If you are okay with that, click on no grid, because now we don't know how many numbers of columns and how many numbers of rows do we have, because the numbers of rows and numbers of columns will depend on the size of our basin or the size of our study area, and also the discretization value, whether it is 100 meter, 200 meter, 150 meter, etc. Unfortunately, it's not specified on the exercise manual how much value are we going to discretize, but let me assume we are going to discretize our model by using a 200 meter by 200 meter grids. So keep in mind that, and click on no grid, no grid. Yeah. So this is the Model Muse window, the MODFLOW graphical user interface. Then next we are going to import the shapefile of our interested area or our study area. So you know where is the locations of your shapefile and where is the locations of those groundwater wells. So import them. First, let me import the shapefile of the study area. So click on File, Import, and Shapefile. File, Import, and Shapefile. The shapefile of the study area for this simple exercise is irrigation unit 4. So add it. Click on Open. When you open the irrigation unit 4 and click on Set Values of Enclosed Cells, that is the first option, and the numbers of the formulas is the whole aquifer. That means from the model top to the lower sandy layer units. So click on 2, and the higher Z coordinate is the model top, the lower Z coordinate is the last aquifer or the bottom of the last aquifer. So the higher Z coordinate, click on Edit and go to Data Sets, Required, Layer Definition, and Model Top. Double click on Model Top. Then OK. The lower Z coordinate is the bottom of the last aquifer, so edit again and click on lower sand unit bottom. Then okay. If you are okay with that, click on OK again. Nothing happened. The study area still is not displayed here because we are not still discretized our area. So to discretize, open the study area on the top window of the Model Muse. Click on object icon here, this one. Click on that. It says unused object. So from this term, you know that we already added the shapefile, but still it's just unused. So maybe expand this unused object option by clicking here, and you will see the file name of your study area, which is irrigation unit 4. Double click on it. Double click on it. Double click on it. When you double click on it, the object window or the object property window will pop up. Then here is the place where you can specify the grid size or the grid cell size. Like I said, we are going to discretize by using a uniform 200 meter by 200 meter grids. Click on use to set grid cell size. And it's just 200 meter. 200 meter. If you want to change the border or the color of your study area, maybe click here on the color object, and maybe I can make it blue, and okay. And it's always good to position lock. By meaning position lock, if you use a pan or any other mechanism, that means your study area will not shift. It will remain as it is. So click on position lock. Then click on OK. Again, nothing happened. Nothing happened. You can see your interested area. To see your interested areas in the grid, click on generate grid option here. Generate grid. Then if you need just a vertical grid, you can uncheck calculate grid automatically, calculate grid angle automatically. But if you need a grid which lies along the direction or maybe the size of your shapefile, so leave it as it is. So maybe let me try calculate grid angle automatically, because last time, if you remember, we unchecked this one. In that case, we do have just a vertical grid. So let me assume like this and click on OK. Now you will have your study area with 200 by 200 grids. This is just the top view, and this is the side view, and this one is the front view. Then if you examine, we do have three aquifers, no? 1, 2, and 3. But as you see, the top surface, it's just flat, and even the bottom surface is just flat. But in real world, there is no maybe a flat surface like this. There may be a topography, a mountain area, or there may be a river, or maybe there may be a depression. That's why we have to set the model top by using the digital elevation model that I already provided you. And the other thing, because our polygon or our study area has this shape, what we are interested is only those grids inside the shape. We are not interested on those grids which is outside. Yes, if you remember last time, those grids outside of our modeling area, they are inactive, and the grids inside our modeling area, they are active grids. So the calculations or the MODFLOW calculation should be based on those grids which are inside our modeling area. So the next step, what we are going to do is we have to specify the active grids. Here, you do have the option in order to see show or hide 2D guidelines or 2D image. If I click here, you do have the options of show all and show active, show exterior, show active edge. Please try to click on each one of them. For example, let me click show exterior. Exterior is the exteriors of your area. And again, let me click on show active. Do you have the same? Do you have the same? Do you have the same? No. When you click on show active, it shows you the whole area, no? Just like this. Yes? To simulate your model top, you have to import the digital elevation models of that specific area. But always, what you have to take care, in Model Muse window, you can import the digital elevation model as a text. For instance, let me try, click on File and Import. Look, the option that you have is a shapefile. If you have a shapefile, you can import it, a DXF file, a surfer grid, sample DEM data, and if you go down, you can see this ASC2 or ASCII2 raster files. I don't know if you guys are familiar with this file format, ASCII2 raster file. This is the well-known text format in ArcGIS or in ArcMap window. If you examine your ArcMap window back again, imports any image files to be used as a model top, you have to convert this digital elevation model into ASCII2 format. To convert into ASCII2 format is very easy, simple, straightforward. That is, go to ArcToolbox. ArcToolbox. There is conversion. Inside the ArcToolbox, you can get conversion. And when you go down, you can get a tool which says from raster. Then click on the plus sign. You can see raster to ASCII2. That's what we are looking for. I don't know if I already provided you the converted ASCII2 format. Please check on the folder. No? No. So if you don't have it, just double click on it. Double click on it. And here, call upon your clip DEM. Click on the down arrow and click on clip DEM. Yes, and specify the output location. Maybe it's better to put it together with the folder that you have it in exercise 4. So click on the browser here and go to your file exercise 4 and save it as ask2dem with the file name ask2dem. In my case, let me go to the locations which says MODFLOW example 4. Here I do have ask to, but let me do it together with you. Ask to, maybe let me add two just to differentiate. Save. Then click on OK. Please remember where is the locations of the converted file. Okay. Then click on OK. Now, as you see here, it's just converting from raster to ASCII2. Because the size is very small, it's done already. But if you use the bigger digital elevation model before clipping, it will take some time. So after having your ASCII2 format, please go to the Model Muse window and import it. Click on File, Import, then Ask to Raster. Yes? Then go to the file that you saved it now. In my case, it's just inside MODFLOW example 4. That is this one. That is this one. That means this file, ask2. I believe you have it also. Then click on open. Click on open. Yeah. Now we are going to set our model top as the digital elevation model. So here it says data set. Click on the down arrow and model top. Model top. Like I said before that, look, the top surface of your model is just flat, yes? But you will see later what is the difference after importing the digital elevation models of this area. So the dataset is a model top, and click on set values of cells by interpolation. And here, which filter methods are we going to use? This depends on, it's just objective judgment. You know, someone may use point closest to cell center, and maybe the other one average of points in cell, and maybe the lowest point in cell. That's just a subjective judgment. But for this specific example, let us select average of points in the cell. That is the default one. Then click OK. Click OK. Click OK. Okay. Now it's just importing the digital elevation model into the Model Muse window. In my case, it says no points were included in 47 cells, so they have been skipped. That's okay. So click on OK. Still now, you haven't seen any change on the top of your model. You haven't seen any change on the top surface because we haven't specified the interpolation method. To specify the interpolation method, click on data, and edit datasets. Enlarge or expand the required ocean by clicking on the plus sign. Go to hydrology. Go to layer definition and click on model top. So when you click on the model top, you can see here that the interpolation is none. So we have to specify the interpolation techniques. So click on the down arrow, and maybe we can specify the interpolations of fitted surface. So you guys are required to read what is the difference between each interpolation techniques. What is IDW, that is inverse distance weight method, what is natural neighbor, rearrest, etc. But for this specific example, let us select fitted surface. The fitted surface. Yeah, then click apply. Look, when I click apply, I can easily visualize a change in my model top. Look here, my model top is not horizontal now. You can easily see that this is not horizontal. Yes, the second and the last layers also should be correlated with the model top. To do that, go back again, data, edit data set, edit data set. Then again, layer definition, click on upper aquifer, that is upper sandy unit, and it's just minus 50 meter, but you have to correlate that the upper sandy unit is maybe model top minus 50 meter. So click in on edit formula, and here you can write model top minus 15, model top minus 15 meter. And again, look here, the bottoms of the second layer, or the top of the second layer is just horizontal, but now when I click OK, maybe it will change. You guys put your eyes here on this red horizontal line. So when I click OK, now maybe there is a change. You can see that, no? And similarly, you can specify and you can correlate the top of the third or the last layer as model top minus again 30, model top minus 30. Then OK, then apply. Again, that one is also changed, and again the bottom of the last layer also is just model top minus 45. Yes, now it seems like, you know, a natural aquifer. It seems like a natural aquifer. It's not horizontal. After having that, the next thing is we have to tell the software which measurement unit are we going to use. If you read the question, we are asked to run a transient model, but that transient model is annual transient model. So click on model and click on model options and click on option again, and the length is in meter, that's okay, and the time units is years because we are going to simulate an annual transient model. So the time unit is years. That's okay. Then click on OK. And next, we are going to specify which package are we going to use, and also the time discretization. We already discretize our model spatially, which is 200 meter by 200 meter. But what is the time discretization? We are asked to run the model from from 1995 to 2006. So we have to specify the time like that. Click on model and go to MODFLOW time. MODFLOW time. We don't have a steady state. We don't have a steady state. We have a transient model only, because we already given the initial height. If you read the question, the initial height can be accounted as, or can be assumed as, the top surface of the model. So our first model starts in 1996. So right here, maybe 1996 to 1997 and 1997 to 1998, and again you can increase until 2000 until 2006. Yes, because we are asked to run the model from 1996 to 1995 to 2006, so the first one should be 1995. Let me do it again. Sorry, this one is 1995 to 1996. Then I can increase. This is 1996 to 1997, 1997 to 1998, 1998 to 1999, then 1999 to 2000, because we are going to run our model yearly, and 2000 to 2001, 2001, then from 2001 to 2002, from 2000 to 2003, and 3 to 4, 4 to 5, and the last one is from 2005 to 2006, from 2005 to 2006, and we don't have the first stress period is not the drawdown reference to. You don't have to check this one. It should be like this. So it means we do have generally 11 stress periods. 11 stress periods. So you can click on OK. Okay. Next, specify which type of package we are going to use again. So click on model and go to MODFLOW package and programs. Yeah. Here on the flow, we are going to use layer property flow package. That's okay. And on the boundary condition, if you remember, we do have general head boundary, and we do have time variant specific head package, and we do have no flow package, evaporation, well package, and recharge package. So we have to check all of them. So click on specified head and CHD, which is time variant specific head package, and go down and click on specified flux, because we do have well package. So again, click well package, and similarly recharge package, and go down and click on the head dependent flow package. Inside the head dependent flow package, we are going to use a general head boundary package, and similarly evapotranspiration package. That is it, I think. And again, you are going to specify the solver also. In my case, I am going to solve this problem by using the MODFLOW program. So there is no problem if I can select maybe PCG, PCGN, SIP, or DE4. But if you guys are going to run your model by using MODFLOW NWT, then you have to change the solver into NWT server. So in my case, let me use SIP, or strongly implicit procedure package. Click on OK. I believe some of you have NWT, MODFLOW NWT. So if you are going to run by using a MODFLOW NWT, first you have to change here into MODFLOW NWT. In my case, it's just MODFLOW OM. But in your case, click on MODFLOW NWT, and then you have to go to MODFLOW package and program, and you have to change into UPW or maybe upstream weighing package. And again, the solver again should be a Newton package. So you have to be taken on that. After having that, we are going to import the shape file for recharge, evapotranspirations, and other packages. But first, let we specify our boundary conditions. Our boundary conditions are the CHD or the time variant constant head boundary conditions because of the Colorado River, and the general head boundary conditions at the south, and the injection well maybe in the north direction, and no flow boundary condition on the west direction. Like I said, I do have the shape file of the CHD and general head boundary package, so maybe I can import it here. So I can click on File, Import Shapefile, and I do have the general head boundary, GHP, then open. This general head boundary is on the first layer, so I can say 2, and it's from the model top to that of the bottom of the upper sandy units. So I can click on OK. Sorry. Yeah, I know. And I can import also the data inside. Then I can click on OK. So that means I already added the boundary condition. That means this one. Let me change the color into red. In that case, it will be visible. That means the red one can be accounted as a general head boundary. In your case, if you don't have the shape file, you can draw. You can draw by using those objects. The first object is maybe create a polyline object. Click on create polyline object and just draw, just dun, along the border. This red line can be taken as the general head boundary. In my case, I can double click on it and I can specify the properties of the general head boundary. I can click on more flow features, and among the package, I'm going to use the general head boundary package. In the general head boundary package, I do have 11 stress periods, so I will use the different 11 stress periods here also. So maybe I can write here 11, so I do have the 11 stress period. Then the starting time, it comes automatically because we already specified in the MODFLOW time. In the MODFLOW time, we already specified our stress period is from 1995 to 2006. So the first is from 1995 to 1996, 96 to 97, 97 to 98, again 98 to 99, up to the last one. Then from 2005 to 2006. To specify the general head boundary, we need to have the boundary hairs and also the conductance value. If you remember, on the GIS window, I already showed you what information do we have inside the general hair boundary shapefile. So maybe I can right click and I can see the attribute table. In this attribute table, the hydraulic head is 86 from 95 to 1000, and it is 100 for the other pairs. And similarly, the conductance is 0.002 from 96 to 1000 and 0.03 from 2000 to 2006. So I can specify those values as it is. So I can go back to the Model Muse window, then I can specify the boundary head. So to specify, open your Model Muse and click on the function here. Click on the function. And here, if you remember, you can specify those values by using the formula. That means by using the function. To specify, click on the function and go to the object and click on object imported values R, which is real number. Double click on it. Double click on it. Yeah. Let me do that. You can click on function, then click on the function icon, go back until you get object, then go down and double click again object imported values R, and here you will specify which value from the attribute table is the head for a general hair boundary condition. If you remember, we already imported the general hair boundary in my case, but in your case, to make it simple, you can write 100. That means you can write 100 down. But you can specify by using the formula function also. To specify by using the formula function, you can click on user defined, created from shape. Here you have the option. From 95 to 96, I can use the head from 96 to 2000. Then OK. Then I can click on OK. It means I already specified the value from 1995 to 1996. Next thing, what I'm going to do is just copy this value. Just copy this one, Control C, and paste here. Control V, again Control V until 2000. Control V. And from 2000 to 2001 and from 2000 up to 2006, it is different. So click again on the function. And again, go to function and object value R, which is the imported head value. Then go back and you can specify the head from 2000 to 2006. Here, if you are correct, it should be displayed here on the upper window. Sometimes it's not, because you have to have this symbol. And again, here also the same symbol. Now it will display on the upper window here. Then click on OK. The next thing is you have to copy this one and paste until the end. With similar manner, you can specify the conductance value also. Click on the function, go to function, then object, again object value R, then go back and select the conductance value for the first period, which is from 1995 to 2000. So double click on it, and like I said, you have to put the symbol for correction, then it will come on the upper window. Then I can say okay. Then I can copy the same value and I can paste until 2000, and from 2000 onward the value is different. I can repeat, I can go to object, then object values are, then the conductance value from 2000 to 2006 is this one. So double click on it, again put the symbol here, then click on OK, copy and paste it for the other stress periods. So with this manner you can specify the parameters of your general head boundary and click on OK. Now you specified the general head boundary values. Again, import the shapefile to specify the constant head boundary. So shapefile, then CHD, which is a constant time variant constant head, then click on open. I can say set values of intersector cells, and I can put it on the layer 1, so it is from model top to the bottom of the first layer, which is at the bottom of the upper sandy unit bottom. Maybe I can change the color into red or etc. and import the data also. The data which are included inside the shapefile is the head from 1996 to 2000. This should be from 1995 to 2000 and 2000 to 2006. So we do have a time variant head value. So I can check this one because I need it later to specify these values by using the function. I can say okay. I can say okay. It's telling him that the following attribute have name, because if you remember when we specify general head boundary we do have the same name. So what am I going to use? So I can say create a new data set with a different name, then okay. Now this is the CHD boundary. Maybe I can change the color. Let me make it the color into red or yellow, and let me make it red. Then that's okay. Let me change to differentiate from the general head boundary. Let me make it yellow. So this boundary is the constant head boundary, time variant constant head boundary. Again, double click on it and go to MODFLOW features, and it's just CHD or time variant specified head package. So here again we do have starting time, ending time, the starting head and the ending head. For this specific example, we assume we do have a constant head value for the whole. That means the starting head is, I can say 100, and the end head is 100 or 88 and 88. When you read the example, it says you can use a values of 100 meter from 2000 to 2006 and the values of 88 meter from 1995 to 2000. So from 1995 to 2000, 88, and from 2000 to 2006 it's 100 meters. So our stress period is 11, similar to the time frame, that is from 1995 onwards. From 1995 onwards. So you can see this one as it is. I know it's just tedious, because you have to specify each and everything just by clicking and also by inserting all of those values. But you have to know how to build a model if you want to be a groundwater modeler. Those is the basic steps, unless you know how to write a program. If you know how to write a program, in that case you are not supposed to use the Model Muse. Just you can write a program. So from 1996 to 1997, from 1990, sorry, again I made a mistake. From 1995 to 2000, the head is 100, sorry, 88, and onwards the head is 100. So you can put those values as it is. So I can put here 88 for not writing. You can write like this, or you can specify by using the function. There are two ways. By using the function means the system SD will call the value of the general, the constant head values from the shapefile. If you specify by using the function, it will know those values. But if you want to specify manually, you can write 88 up to here, and from 2000 to 2006 is 100, again 100, again 100, 100, and 100, and the ending head, which is similar to this one, because we assume a constant head value. So I can say that one, or you can specify by using the function window. The function window is very useful because if your data is very big, it's difficult to specify manually, For example, on the well package, we do have so many wells and also so many informations. In that case, it's difficult to write all the values on the window. Rather, you can specify by using the function. So we already put the general head boundary and the constant head boundary. Now we are remaining with the injection well. Again, in the north we do have one injection well, so we can put that injection well. So to put a well, just click on a point object. That is a point object, and you can put it maybe somewhere in the north direction. So let me put it here, or you can put it wherever you like on the north. I can position lock, and this is just on the top layer, and the MODFLOW features, click on the MODFLOW features, that is injection well. By meaning injection well, we are injecting water toward our aquifer. In that case, the pumping rate is positive. The pumping rate is not positive. So the time is for the whole time from 1995 to the last stress period, and the value is the value which is given here. That means this amount. So you can copy and paste here. Click on OK. Now we are going to import the wells for a well package. If you remember, we do have so many groundwater wells around 95, 96. That means those points. So import them. Click on File. Then go to Import Shapefile, and you remember where is the locations of well.shp. It's just in my case inside extraction well 95 to 06.shp. You have it inside your folder. Double click on it and click on the well and open, and click on set values of intersector cells, and all of the wells are on the top layer, on the first layer. So click 2, and the higher Z coordinate is the model top, and the lower Z coordinate is the upper sand unit bottom. And here you can also check what data do you have inside the shapefile. So click on data here. Look, you have the location and also you have the extraction values. If you remember, F4 is the extractions for the year 1995, and F15 is the extraction as the last stress period, that is the extraction at 2006. So select all, click on select all, and click on OK. Click on OK. And it's telling me that there is the following attribute have that my existing data, so I need it with a different file. Look, those are the groundwater wells that you saw here. Those pointers are coming here. So let me check those groundwater pointers, and let me specify the MODFLOW features. If you need, you can change the color into red, I don't know, or maybe any other color. Let me make it red. And go to MODFLOW features, and specify by using a well package again. Here, in this case, you don't have 11 stress period because from 1995 to 2006. So the first one is from 1995 to 1997. Sorry, 1996 to 7 until the end. Yes. Yeah. So this is a very important step. Look, if you remember, if you go back to your shapefile in ArcMap, and when you see the attribute tables of the groundwater wells, we do have lots of information or lots of extraction values. Imagine in 1 year, in 1995, we do have 95 wells, and each well has its own discharge. For instance, the first well has minus 6064.88 discharge value. So you don't have to write all of these values manually. You can't. So what are you going to do is you have to specify all those values by using the function window in ModelMuse. But keep in mind that the pumpage for the year 95 means F4 colon, and the pumpage for the last year 2006 is F15 colon. No? If you are okay with that, go back to your ModelMuse window. And specify the Aquifer pumpage for each well here. For example, for 1995, that's F4, and at the last year, which is at 2006, it is F15. So click on the function here, and go to function objects, because you already imported those attribute table. Then you can have object value r, and here it should be f4. f4 means this column. f4 means, if you remember, the column in the attribute table, that means all of these values, all of these values. Where to find f4? Go back, and it's just on the imported file, on user defined, and find f4. Here we can get f4. So double click on it. When I double click on it, it will come and join here. So double click on it. Like I said, you can put, this, I don't know, it's called, what's called in English, this symbol to be correct. Then it will display here. Then click on OK. Now the system will understand for all groundwater wells, the pump page from 1995 to 1996 is the column F4. And similarly, do the same for the other part. So for me, to make it very easy, I can copy the first here, and this F4 will be F5, and again I can copy here, and this one should be F6, and similarly here, this is F7, and until the last one. This is F8, here this is 9, this is 10, this is 11, 13, this one is 14, and this one is F15, this one is F15. Yeah, now I already tell the software what is the amount of the extraction. For example, at the last year is just F15. By meaning F15, all the values of the column 15. Then after that, I can say, okay, now I do have my wells. Well, still we are remaining with the other package like recharge package, evapotranspiration package. So to determine the recharge and evapotranspiration package, always it is good to import the original shapefile of the study area. So go to file, import shapefile, then I can import the shapefile of the study area, open, set values of enclosed cell, and I will use recharge package, so I can put it on the top surface. So it's just one, and it's just model top. It's just model top. So model top. Yeah, on the model top. Maybe I will change the color later for a better visualization. That means I do have another layer on the top. I can double click here, and let me change the interior color into here. And the MODFLOW feature is the recharge package. On the recharge package, it's specified on the example that the recharge rate is 3.8 times 10 raised to minus 9, and the recharge location is top active cell. So I can put the time from 1995 to the last stress period, 2006, and the recharge rate is 3.8 times 10 raised to minus 5. That's okay. So I can say okay. Then I do have also the evapotranspiration passage. To specify the evapotranspiration package, again you can add the same shapefile, or maybe you can use the already imported shapefile. But let me add the same shapefile, and I can use that one as evapotranspiration package. So I can put it again on the first layer because it's just evapotranspiration. Sorry, from the top to the upper sandy unit bottom. I can say OK. And let me change the color for the evapotranspiration. The color, maybe let me make it a little bit of this one. And the MODFLOW feature is EBT, or evapotranspiration. Again, if you check the example, it says on the evapotranspiration package, the evapotranspiration rate is 3.17 times 10 raised to minus 8. So it should be from 1995 to the last stress period. Then the rate is 3.17 raised to minus 8. And the evapotranspiration surface is the model top. So here, check, and this is just a model top. And the evapotranspiration depth should be 0.5. It's just given on the exercise. So I can say OK. Now I already specified the evapotranspiration package, the recharge package, the general hair bindery package, the well package, the injection, and also the constant head package. The next thing what I am left is to specify the aquifer properties. Still, we haven't specified the hydraulic conductivity values. Because if you remember, on the example, it's given that the hydraulic conductivity for the top layer is 3 times 10 raised to minus 5. The middle layer is 10 raised to minus 3. And the last layer is 3 times 10 raised to minus 5. So we have to specify the hydraulic conductivity values. To specify that one, click on data, then edit data set, expand required hydrology kx. If you remember on the example sheet, the kx value for the first layer is given as 3 times 10 raised to minus 5. 3 times 10 raised to minus 5 meter per second. Yeah. So if you remember here, on the top layer, the K value is 3 times 10 raised to minus 5. For the middle layer, 10 raised to minus 7. And for the third layer, 3 times 10 raised to minus 5. So we have to specify all these values. So to do that, click on data, edit data sets, and required hydrology kx. So kx for the first layer, 3 times 10 raised to minus 5. So maybe we can write 3e minus 5. And for the second layer, it is just 10 raised to minus 7. So maybe you can write 10 raised to minus 7. Sorry. Let me do it again. Okay. Let me do it again. Those values, they are kx values. That means the horizontal hydraulic conductivity. That means the horizontal hydraulic conductivity for the first layer is 3 times 10 raised to minus 5. For the second layer, 10 raised to minus 7. For the third layer, 3 times 10 raised to minus 5. And it says that also it's just hydraulically homogeneous and isotropic. It means kx is equal to ky. But the kx value for the third or for all 3 layers is different. So how we can do that? That means we have to specify only kx, and ky is equal to kx. That's okay. So how we can write? Because we do have 3 values for the first layer, second layer, and third layer. So how we can do that? You should have we have to edit formula and we have to create a case. That means if. That means if it is for the first layer, use 3 times e raised to minus 5. If it is a second layer, 10 raised to minus 7. And if it is a last layer, 3 times 10 raised to minus 5. So how we can do that? Click on edit formula, and go to function, and go to logical, and it's just case. Guys, this is very important step. So double click on case. That means I'm going to create if function case. So the index here is a layer, no? The index is a layer because layer 1, layer 2, layer 3. Where to find the layer? You can find the layer inside grid or mesh option. Expand this one and you have layer. When I double click here, it will come here. So I can double click here. Now I can write the result. For the first layer, it's just 3 e raised to minus 5. For the second layer, it's just 1 e raised to minus 7. And for the last layer, it's just 3 e raised to minus 5. So the system will understand the first layer is 3 raised to minus 5, the second layer is 1 raised to minus 7, and the third layer is 3 raised to minus 7. And like I said, always, when you write a formula, it should be displayed here. If it is correct, it should come up and display on the top window. Now it's not, so maybe because of those 3 dots, maybe you can reduce the dots like this. You know those things, when you exercise this MODFLOW, ModelMuse, etc. Now it's just displayed. It means the argument is correct. So I can click on OK. That means the first layer has this hydraulic conductivity, the second layer, and the last layer. KY is just isotropic and homogeneous. That's okay, and also KZ. That's okay. And we also provided that the MODFLOW initial head can be taken as the top model. If you read the example problem, it says run the annual transient model from 95 to 2006 by assuming the initial head as the model top. So the initial head, the model initial head is the model top. So go to edit formula and click on model top, required layer and model top. That means the initial head can be assumed as the model top. And also it's provided on the sheet that the specific storage is 8 raised to minus 2. Always, again, you have to keep in mind that if you are running the steady state flow, you don't have this option, specific storage. Check it, or in the previous exercise, maybe you already noticed it. When you run the steady state, this specific storage option will disappear. But if it is a transient, because in that case you have a storage, that means in the flow equation, the right side of the equation exists. So that's why specific storage is required. So on the paper, it says the specific storage can be taken as 8 times e raised to minus 2. So I can write here as e raised to minus 2 and apply. So what's remaining is the aquifer type, whether our aquifer is confined or a convertible layer. So for this specific example, let we assume the first and the second aquifer is confined aquifer, convertible aquifer, and the last layer is a confined aquifer. In MODFLOW or in any modeling, groundwater modeling, by meaning convertible, the system will determine whether that aquifer is confined or unconfined based on the calculated hydraulic head value. So let me assume the first and the second layer convertible and the last layer is confined. So to specify that one, click on model and go to MODFLOW layer groups. Here you have the upper sandy layer or the upper sandy unit. Let me make it convertible, and The middle one, or the silty clay unit, again this one is convertible, and the last one, let me assume, is confined. The last one is confined because you know that it's between a clay layer. Yes, because if you see this one, the middle layer is silty clay unit, and the base is again a clay. You know that clay is impermeable material. In that case, it's just a confined layer. That means the last layer is a confined layer. But let you assume the first and the second as a convertible layer, the system will calculate here and will determine whether they are confined or unconfined. So when you finish, click on OK. I believe we already have all the inputs information, so maybe we can save our model and we can run the model, and we will see what will happen if the model converge or if not. Maybe some of the data or some of the informations are arbitrarily. Maybe we will face some difficulty in convergence, but we will change some parameters and we will see what will happen. So always before running your model, if it is a project or a research work, it's always recommended to save it, because you know we already take around 2.5 hours, so all the work of this 2.5 hours will lost unless you save your file. So I can save my file. I can go to save file, save as. So maybe I can put it here with the file name exercise 4, maybe exercise 4, and save, then save. So next I will run the model. Like I said, if you use MODFLOW Newton, you can run by using MODFLOW Newton if it is ohm. In my case, I will run my model by using MODFLOW ohm. So I can click on here, run model, and exercise 4 is okay. Then save. Then yes, it's just running, and we will see what will happen. Let me show you what's happening. There are some percent discrepancy problems, but that's okay because I don't have any warning. I don't have any errors. That's expected, you know. Yeah, so those are yeah, I do have error also. I do have error also. Let me see what error do I have. Let me see. On the error, it says no imported data exists in the object DHP1 for the following names. It means okay, I can do that. And no imported data exists in the object 6 for the following names. Now, so let me put this one manually. This is a general head boundary package, so I can come up here on the general head boundary package, and I can do the same. This is a general head boundary package. It's just telling me that those imported values is not visible. So let me do it manually. If you remember, it was just 100 and area, so I can put it 100, and here also 100 until 2000, 100, and from 2000 I can say it's area. And similarly, the conductance value, it was 0.002, again 0.00 to here, and for the last one it was 0.03. Then I can say okay. And I do have also another error. It's telling me that on the well package, the imported pump page, they are not imported well. It's telling me that. That means it can't find this F4. It can't find this F4 value. So let me do, and let me run again the model. In this case, you can see the values of the normal terminations. That means you can check your outputs. To check the outputs, you do have a list file. That means this one. This is a list file. On this list file, if you go down, you do have 11 stress periods. For each and every stress period, we have the water budgets. For instance, the water budget for the last stress period, that means for the 11th stress period, is this one. You have inflows and you have outflows. As you see here, on the inflow sections, you do have I can see some error because we have so many wells, but the values of the well is not displayed because of when I imported them, maybe it was mistaken. But you can see that the percentage discrepancy is around minus 0.01. It means it's okay. It's okay in my case, but it needs some correction again in order to make. Yeah, I believe you already grasp something from this exercise, how to build a MODFLOW model, how to run, and maybe lastly how to see those results by using the list file. And that's what I have for today maybe.